Dear friends, students and learners, I am Dr. Shashank Shrivastava from the School of Engineering and Technology, Indira Gandhi National Open University, and I am offering the course Material Science under the Swayam portal. So the first module which I am going to discuss with you and this is mechanical properties of materials. It will be divided in about 4 to 5 lectures. I am discussing with you the part 1 today. So I will discuss the objectives of this particular module, and actually here all the objectives are listed, which comprise of 4 lectures. The first one will be the effects of force in solids, both qualitatively as well as quantitatively you would be able to know. Then you will be able to analyze the compression test, know about the universal testing machine, and understand tensile strengths and effect of strain rate. But in this particular module you will be knowing only up to the tension test, simple tension test, and certain number of properties. So when we talk of mechanical properties, actually, so it comprises of different things, like some examples are given here: strength, elasticity, ductility, toughness, stiffness. All these things you will be able to know, and you will be able to gauge the strength and the behavior of the material under different conditions, and thereby decide the suitability of a material for a specific job. So as I discussed before about the mechanical properties, and we need to determine them. So what we have to do, there are certain tests, and basically there are 2 types of tests: the static and the dynamic. By static, actually what you mean, there is no time element in that, whereas in dynamic the time element comes in. In a static, we are applying the load very slowly actually, and sometimes it is also mentioned as quasi-static. That's why it is called quasi-static, because the load has to be applied very slowly, so that we can call that it's almost static. And the other one is dynamic, which we are not discussing right now. So how to determine the mechanical properties? Actually, when we talk of mechanical properties, then we should also know the ways to determine the mechanical properties. So there are different ways. The static ways are there and the dynamic ways are there. So common static tests are like the axial tension test, where what we do is that the force is applied along the axis of the specimen. In case of compression loading, same thing is done, and force is applied along the axis but in the opposite direction. The third one is the flexural loading, which is also called the bending effect. So the load is applied perpendicular to the axis. And the fourth and final test is of torsional loading, where the load is applied but not according to the bending, it is in an eccentric direction and transfers to the specimen. So here are certain visual things through which you can understand better. So the first one you can see axial tension and compression. So there is a bar or a cylinder, you can say. In the first one the compression effect is showing, and the second one it is showing tension effect, where the pull effect is there, and in case of compression the push effect is there. Then the second figure you see is that of torsion, where twisting effect will be there, and further the third one will be about the bending, where the load is acting perpendicular to the beam or the specimen. So if you want to see the bending effect, I will just tell you with the help of this scale. You can see here, see the load will be acting like this and the scale will be bending. So the load somewhat will be acting like this. If I place this chalk like this, and this will bend like this. So this is the bending effect. Then this chalk is there, if you can see. If I am twisting it like this, it breaks because it's a brittle material, but this is the twisting effect. Similarly, in case of my wrist, if you see, if I do like this, then this is the twisting effect. And tension and compression, what it is, I will just show you here with the help of this chalk. Tension, you see, I am pulling this like this. This is tension, and when I am pushing like this much, so this is compression effect. So these are the things which we have discussed in the previous slide as well. So now we discussed before this that to determine the mechanical properties, what we have got to do. We have got to do certain number of tests, So we discuss about the static and the dynamic tests. And so the first test which we are going to discuss is the simple tension test. And the requirements for the testing are as such. First of all, we need a material testing laboratory. Then there is a protocol which is named as ASTM D638 that has to be followed. And the machine name which is being used is generally simple tension testing machine or the universal testing machine. And this machine can be hydraulically powered through a fluid or electromagnetically powered, meaning through electric current power will be given. And the final thing, we all know that a specimen has to be there to be tested. So what is the purpose of this test? There are a certain number of purposes. The first one is that we want to select a material or item for an application, because there are different kinds of applications. Like suppose there's a toy car, then you use a certain plastic which is not very strong, but when you are driving your own car, that car has to be of greater strength so that it can survive crash test as well. So different kinds of materials have to be used at different places for different functions. Then we have the purpose of predicting how a material will perform in use, normal and extreme forces. Then to determine or verify the requirements of a specification, regulation or contract are met or not. And we have to decide if a new product development program is on track or not. Furthermore, purposes are there. Proof of concept, like we have to display some proof of concept. We are doing certain research, then we have to display the proof of concept, whether it is conceptually right or wrong. So one purpose of this test is also that. And then the utility of a proposed patent. Somebody has filed a patent, then we have to see what is its utility. So we can use the simple tension test for that purpose. Then provide the standard data for other scientific, engineering and quality assurance functions, and providing basis for technical communication. And then finally providing a technical means of comparison of several options. So when we do the tension test, we should also know what are the capabilities of my machine. So four most important parameters for this are: the first one is the force capacity, meaning machine, how much the machine will be able to generate the force, what force it can generate, and so that we can know which specimen it would be able to fracture or not. Further, speed, the rate at which this force is applied, that should be also known. Whether the test is being carried out very quickly or is it done very slowly enough to perform the actual application. And further, precision and accuracy, for all kinds of tests we need that it should be precise as well as accurate. And for that purpose, measurement of gauge length and forces applied is also very necessary. And what is gauge length actually? Gauge length is the distance between 2 points on the specimen, which we will be able to see in the figure also, which will be coming up in the slides further. And finally, measurement of these parameters is of utmost importance, since a machine designed to measure long elongations may not work for a brittle material. So what does the testing machine actually have? It has suitable devices and holders. For what purpose? To hold the specimen so that perfectly axial load can be applied on the specimen. So like I showed you in the demonstration, that how a tensile load is acting or a compressive load is acting. So tensile load always acts in the axial direction, and if it doesn't act in the axial direction, then what will happen actually? So bending effect will happen and it can destroy the specimen. So that's why the question arises, why alignment is so important. So alignment of the test specimen in the testing machine is very critical, because if the specimen is misaligned either at an angle or offset, then the machine will exert a bending force on the specimen, and then we will get vague results and we will not be able to get the material properties, especially in case of brittle materials. So what is the solution to avoid this bending effect actually? So we will use spherical seats or U-joints between the grips and the test machine. And how can we know about this misalignment? We can know when the initial portion of the stress strain curve is curved and not linear. Generally in the stress strain curve, in the initial portion the curve is linear, but when it is misaligned then it will not be linear, it will be curved. And when I am talking about stress and strain, now strain measurement is coming. So let me tell you about stress and strain as well. So what is stress? Like a force is being applied on a certain object or a certain body, then it tries to resist that force. Like suppose my hand is there and it is attached to my body through this collarbone, then if somebody pulls it from the other direction, so it will try to resist, and this resistance is causing the stress. And strain is what? If this hand pulls out, then it is a strain, the elongation is coming in, so that is a strain. So these are the two things, stress and strain, which have to be understood. So how to do this strain measurement? Strain measurements are done with the help of extensometer, but strain gauges are also extensively employed, especially in case of small test specimens. And another way is that machine itself can record the displacement between its crossheads. Actually, I am going to show you the machine, the figure. There you will understand what is crosshead. So before starting with the simple tension test procedure, we need to prepare the test specimen. So how it is done? It depends upon the purpose of the testing, first of all. Then a tensile test specimen has a section in between and shoulders at the end. So if you can say, like, it is a kind of a dumbbell. If you have seen a dumbbell, so in the middle portion it is somewhat thinner, and at the end there are two more portions which have more diameter, and it will be shown in the figure also in the coming slides. So the shoulders are large so that the specimen can be easily gripped in the machine. So shoulders are meant for the purpose of gripping the specimen in the machine. So the gauge has a small cross section, meaning the middle portion has a small cross section, diameter is less, so that deformation and failure occur in this area. Okay. So when we talk about the specimen preparation, so first of all we also need to know about how we are going to hold it in the machine. So there are different kinds of grips. The first one is the serrated grip. The advantage is that it is cheap and easy to manufacture. The disadvantage is that alignment is dependent on the skill of the technician. The second one is the pin grip, where the alignment is very good, but again it requires skilled labor to manufacture that. The third one is the threaded grip, and it has the advantage of good alignment, and the technician must thread it to one diameter length of the specimen, meaning the technician is skilled, that much is not required, but the preparation before that is very much required. That specimen has to be threaded up to one diameter length of the specimen. Now here you can see the different kinds of grips. There is A, B, C, D and E type of specimens. The first one you can see is the threaded grip. The second is the serrated wedges type. The third is the split collar, and again the serrated wedges type, where pin is also being used. So in the specimen you can see now here, which I told earlier, that it has shoulders at the end and the middle portion is thinner, the dia is less. That upper portion, the shoulder, is used for holding this specimen in the machine. So the test process now we will discuss, and we will see that the machine, when it starts, it begins to apply a slowly increasing load upon the specimen. This is very important, because if we apply the load in different manners, different types of results will be coming. So after that, what will happen? Once we apply the load at a certain rate, then at a specific time intervals, reading of the load and elongation of the specimen are recorded. Increase in tension can be observed through the bare eyes as well, but we also have the extensometer for measuring the strain. As the extension begins to increase at a faster rate, then the extensometers, if attached, shall be removed. So with further increase in the load, as the load increases, the extension increases at increased rate, and record of extension may be obtained from displacement between the crossheads. At some level, the load becomes stationary and the specimen either fails or begins to reduce in cross section rapidly. So this phenomena is known as the necking. Necking phenomena is happening. Necking is followed by reduction in load accompanied by further extension until the specimen fractures into two pieces. So here is the simple tension test machine. Now I will explain it to you. I talked to you about the crosshead. So you can see here the fixed upper crosshead and the fixed lower crosshead. These are the two things. Then further you see the grip or the holder is there. It is meant to hold the specimen. You can see on coming towards the bottom side, the tension specimen is there with lesser diameter. This is the main portion. Then the end portion has larger diameter. Then the screw column is there. This is meant to move this is the moving crosshead. You can see there is one labeled moving crosshead in the diagram. That is moving, not the fixed crossheads. So to move these, a screw column is required. And a space for the compression specimen is also there. So both kinds of tests can happen here, compression as well as tension. Right now we have discussed the simple tension test. Okay, here you can see the specimen which is subjected to tensile force. See how I am pulling this. I am pulling this and the stress is being acted upon this material, and you can see the diameter, the middle portion is lesser, whereas the end portions the diameter is more, like in our specimen, the tensile specimen which is placed between the machine grips. So similar to that, and now I am pulling, and after pulling what will happen, this necking will take place, and finally fracture. So this is the process of the steel specimen also, which is there in the machine. So what are the results of this tension test? The results are that it can be entirely presented in a stress strain diagram. I have explained to you what is a stress and what is a strain. So the results of this tension test can be entirely given in the form of a stress strain diagram. And in the stress strain diagram, the stress is plotted as the ordinate and the strain as the abscissa, meaning the x-axis will have the strain and the y-axis will have the stress. So the stress in this stress strain diagram is the engineering stress that we have to understand. It is not the true stress. But in reality what happens that the area of cross section of the specimen changes. So we need to know about that kind of stress also. So there are two kinds of stress. One is the engineering stress, that is the nominal stress, and the other one is the true stress. So here are the mathematical relations and the definitions where you can understand what is the difference between the two. So engineering stress is given by the load applied upon the area of the cross section, original area of the cross section. You have to understand that the area is the original area of cross section, and in case of the true stress you can see the load upon current cross sectional area, because necking is happening, so the area of cross section is changing, and that current cross section of area will be there in true stress. So the denominator in case of the true stress will be different than the engineering stress. As I told you, P is the load. In these equations, A naught is the original cross sectional area and delta L is the change in the length of the specimen. That is about the strain thing, engineering strain. It can be represented by delta L by L naught. So delta L is the change in the length of the specimen while load changes from 0 to P, and L naught is the original length of the specimen. So this is about engineering stress and engineering strain. So the stress strain diagram, so there are two figures which I will explain to you, and they show the typical stress strain diagrams for common engineering materials. So the first diagram is for the ductile materials and the second one is for the brittle materials. So first of all, what is a ductile material? Ductile material is something which can be drawn into wires. So it is not going to break when the stress is applied immediately. It changes, it slowly and rapidly elongates and finally breaks at a certain point. Whereas the brittle material, as soon as you apply a certain kind of load which it cannot bear, it will break immediately. So this is the difference between the ductile and the brittle materials. It can be seen that a ductile material shows considerable deformation before it fails, while a brittle material shows little deformation. This is the difference between the brittle and the ductile materials. Also, for brittle materials, the strain is less than 5% at fracture, and for the ductile materials, the strain is more than 5% at fracture. So this is one more difference between the brittle and the ductile materials. So here are two diagrams, and these represent the stress strain diagram for ductile materials. The first one is type A of ductile materials, and the second one is the type B of ductile materials. So now we discuss the first type, A. So you can see here on the abscissa or the x-axis, strain is there, and on the y-axis or the ordinate, stress is there. So now you see the curve. In the curve, stress and strain are varying linearly up to a certain point, which is given as A. So that means that there is a linear variation. As stress is increasing, the strain is also increasing in a linear manner, but the rate is not that high, meaning the strain is not increasing at a very high rate. After point A, what will happen? The curve will change and the linear relation will go away, and you can see it is somewhat bending. It is a curve type of portion, and up to D it is going like that. But in that portion, one thing has to be noted from A to D, that the stress is increasing at a slow rate, whereas the strain is increasing at a higher rate. You can see in that figure. And at point D, after that point D is reached, it is the ultimate stress, and thereafter the stress will not increase and it will go down. And as it goes down, it reaches to the point E, and this point E is termed as the fracture point. But in this portion, from A to D and from D to E, you can see the stress variation is not very high, whereas the strain variation is very high. So one more very important thing that we need to understand in this figure is that from O to A is also called the limit of proportionality, meaning again that it's a linear relation. After that, still elasticity is there up to a certain point, like you can see with the curved line, that it is representing elasticity, meaning the specimen after being loaded, when the load is removed, it will come back to its original position without any residual strain. But as soon as that point is crossed, meaning the limit of elasticity is crossed, then yield point comes in where plasticity begins. So after that, if you unload, then what will happen? Then residual strain will remain. Now we will see the figure B. It will be similar to the figure A. The only difference here is that after reaching point A, the graph comes down somewhat up to point C. Why? Because here there are two yield points. One is known as the upper yield point, the one which is higher, and the other one at C is known as the lower yield point. And this is happening because of the movement of the crosshead of the machine. The ends of the specimen which are gripped in the machine are moving slowly with respect to the deformation that is taking place inside the specimen. That's why two yield points are there, and it happens only in certain kinds of materials. So the type B is different for a certain kind of materials, and type A is for a certain kind of materials like aluminium and all, but both are ductile. Okay, so as I discussed before, the type A and the type B of ductile materials. So type A, again here it is given steels, aluminium alloys, copper alloys, etc. And the type B are mild steel and structural steels. So the details which I have explained here are again given, that stress and strain vary linearly up to point A in both cases, type A as well as B. So this region of deformation is elastic in the sense that if load is removed at any point before reaching point A, the specimen will regain its original length and area of cross section. And this is happening for both the materials, the type A as well as the type B. And now what happens in type A after the point A? in the figure. Beyond point A, ductile material changes the relationship, which is more linear. During this deformation, the strain changes at a faster rate than stress, although this rate tends to decrease. This is for the type A of material. And type B material, now the difference comes in. So we can see that in case of type B, the stress drops suddenly to a certain point C in the figure, remains approximately constant over a certain range, and then follows a pattern similar to that of type A. So this is a little difference between type B and type A material, ductile materials. Okay, so as I discussed before, to convince you more, now I am discussing the same thing again. The sudden drop in stress from B to C, increase in strain from C to C dash, while stress remains approximately constant, is known as yielding. And the point B from which the stress drops to point C is known as upper yield point, while point C is known as the lower yield point. The deformation at approximately constant stress is termed as the yield deformation. Once a ductile material has exceeded the elastic deformation, it enters into plastic deformation range. During this deformation, the stress reaches maximum value at D when necking in the specimen begins. So we have to understand that the yield deformation is happening. After the lower yield point, there is a certain kind of deformation, and further it goes up and necking takes place, and then fracture takes place. So the stress at point D, the engineering stress, is termed as the ultimate tensile strength, which is a very important property, meaning the necking has happened, it has reached the ultimate stress, meaning the stress which it can bear. That is the max level of stress which that particular material can bear. This is what is the understanding about the ultimate tensile strength. But still it has not broken. Now the stress will come down. If loading is continued, the specimen fails eventually at E, and stress reduces from point D to E. The stress at point E is called the fracture stress. So the point E is the point of fracture. So in this lecture, we have discussed about the simple tension test, the simple tension test machine, the purpose of the simple tension test, and we also discussed about the stress strain diagram, and we covered up to the ductile material stress strain diagram.